Hello everyone, my name is Tamara Al-Sheikh and today I'm going to be explaining gluconeogenesis. So to begin with, why does gluconeogenesis occur? Well, gluconeogenesis occurs to supply glucose to vital organs that need it, like red blood cells, the brain that largely depends on it, and the testes and other vital organs. So gluconeogenesis is induced during hypoglycemic states. Hypoglycemic states are states when sugar is low in the blood. These states trigger the making of glucose, which is gluconeogenesis, so that these organs don't die out and they have continuous supply of glucose. So when do we need gluconeogenesis? Well, gluconeogenesis isn't always under control. It starts working significantly after 12 hours of fasting, and it's the primary source of glucose after 2 days or 48 hours of fasting. Well, what is gluconeogenesis and how does it occur? Gluconeogenesis, gluco means glucose, neo means new, and genesis is the making. So gluconeogenesis is the making of new blood sugar. And it's basically predominant in fasting states. So it's the synthesis of glucose from non-sugar precursors like lactate, pyruvate, and glucogenic amino acids. How does it occur? We're coming to that. I'm going to briefly go through the steps of glycolysis. It's important because gluconeogenesis is the exact reverse of glycolysis. I'm only going to briefly go through the steps because glycolysis is beyond the scope of this lecture. So, glucose becomes glucose 6-phosphate, and glucose 6-phosphate becomes fructose 6-phosphate, which becomes fructose 1,6-bisphosphate, which becomes glyceraldehyde, which becomes dihydroxyacetone. Now, an important thing is dihydroxyacetone can come back and become glyceraldehyde. This is very important, and I want you guys to remember this. So glyceraldehyde becomes 1,3-diphosphoglycerate, which becomes 3-phosphoglycerate, which becomes 2-phosphoglycerate, which becomes phosphoenol pyruvate, which becomes pyruvate. We have 3 irreversible steps in this pathway. These 3 irreversible steps have to be bypassed during gluconeogenesis, which is the exact reverse of glycolysis. These 3 irreversible steps are steps number 1, number 3, and number 10. So, they're the steps where glucose becomes glucose 6-phosphate and where fructose 6-phosphate becomes fructose 1,6-bisphosphate and where phosphoenol pyruvate becomes pyruvate. So, I'm going to further explain gluconeogenesis. As we said, gluconeogenesis comes from non-sugar precursors and as we said, like lactic acid. So, in order to bypass the first irreversible step, pyruvate goes to the mitochondria and becomes oxaloacetate with the help of the pyruvate carboxylase enzyme, which needs acetyl-CoA to function. So, pyruvate goes to the mitochondria, it becomes oxaloacetate with the help of pyruvate carboxylates that needs acetyl-CoA. Now, for oxaloacetate to leave the mitochondria, it needs to become malate. So it goes from pyruvate to oxaloacetate to malate that leaves the mitochondria. And then back to oxaloacetate outside the mitochondria. So the malate step was just for it to leave the mitochondria. And then with the help of the enzyme phosphoenol pyruvate carboxykinase or PepCK, oxaloacetate becomes phosphoenol pyruvate again. So we have now bypassed the first irreversible step of glycolysis. Oxaloacetate became phosphoenol pyruvate. Now we have the second irreversible step, which can be bypassed with the help of the enzyme fructose 1,6-bisphosphatase. So fructose 1,6-bisphosphate becomes fructose 6-phosphate with the help of the enzyme 1,6-fructose 1,6-bisphosphatase. So we have now bypassed two of the three irreversible steps of glycolysis. Now, in order for glucose to leave the cell after it has went up the glycolysis chain, through gluconeogenesis, of course. So we have glucose 6-phosphate that needs to become glucose. Well, glucose 6-phosphate can't leave the cell because it's phosphorylated. So what happens is it goes to the smooth endoplasmic reticulum where the P is taken. So it becomes dephosphorylated in order for it to leave the cell. I know that was a lot, so I will catch it up for you guys. So as we said, in the mitochondria, pyruvate becomes oxaloacetate with the help of pyruvate carboxylase. After it leaves the mitochondria, oxaloacetate becomes phosphoenol pyruvate with the help of PepsiK enzyme. And then we bypass the first step. In order to bypass the second irreversible step, we need the enzyme fructose 1,6-bisphosphatase. And then we have the final step, which gets bypassed by dephosphorylation, which is the removal of the phosphate, as you see in this diagram. Now, the second source of glucose in gluconeogenesis, triglycerides. Well, if you recall, triglycerides are made of glycerol and fatty acids. So, when lipolysis occurs, triglycerides become glycerol and fatty acids. So, glycerol, if we focus here, glycerol becomes G3P, which becomes dihydroxyacetone. So as I told you to remember before, dihydroxyacetone can become glyceraldehyde again. So if glycerol becomes G3P and becomes dihydroxyacetone, it can go back and become glyceraldehyde, which can go up the gluconeogenesis chain. And by this way, I have reversed the steps of glycolysis with the enzymes I know and the ways I know to leave the cell. So what happened here, to recap, is that triglycerides gave me glycerol and fatty acids. Glycerol became G3P, which became dihydroxyacetone, as you see over here. And then dihydroxyacetone became glyceraldehyde 3-phosphate, as I told you to remember. Now, the third source of glucose is glucogenic amino acids. First, I just want you to know that this pathway is not very significant, but amino acids can become acetyl-CoA, or they can become alpha-ketoglutarate, or they can become succinyl-CoA or acetyl-CoA, and by this way, they can go become oxaloacetate, and then they can go back to become phosphoenol pyruvate and go up the steps as we have already stated. Finally, the clinical correlation. Metformin stops the action of gluconeogenesis. While metformin is a medication used in diabetic patients that suffer hyperglycemia, which is increased glucose in the blood. So, metformin stops gluconeogenesis because gluconeogenesis makes sugar in the blood. So, we don't want extra sugar in the blood. That's why metformin stops the action of gluconeogenesis. Thank you guys for watching. These are my references, and thank you.